Hello students, welcome to the digital learning of session 1 of the unit group of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 1, let us discuss about the definition of the group and abelian group and the properties of group and abelian group. Firstly, let us take the definition of the groups. A non-empty set G with binary operation star is said to be a group if it satisfies the following axioms. So it should satisfy with the four axioms, that is closure law, associative law, law of identity and law of inverse. Closure law means for all AB belongs to G, then A star B belongs to G. So associative law, for all ABC belongs to G. Associative law means we have to consider three elements, that is ABC. Then in associative law, we have to concentrate on the brackets. So here A star of B star C is equal to A star B of star C. Bracket in the LHS side is for B and C. In the RHS side it is for A and B. So star means it is both for the operation, addition and the multiplication. That is, in place of star we can take up addition or the multiplication. Then law of identity. So here identity element we are considering is E. For all A belongs to G, then there exists an identity element E belongs to G. Then A star E is equal to E star A is equal to A. That means here the identity element is E. If E is introduced or operated with any element, here the element operated with is A. Therefore my answer we are getting is A only. So that means E is acting as a supporting character for A. Then law of inverse or existence of inverse. For all AB belongs to G, there exists an element A inverse. So we are concentrating on the law of the inverse here. We are taking the inverse element of the A, that is A inverse, which is also from the group G, such that A star of A inverse is equal to A inverse star of A, which is equal to E. So this operation we have to concentrate or we have to remember for throughout the group. Wherever we are having A star A inverse or A with the inverse element of the A, that is A inverse. A inverse means 1 by A. A and A get cancels, we will be getting it as 1 in other operations, but in the group we are going to get it as a E here. Then finite group. A group G is said to be a finite if it contains the finite number of elements. So in the group it has to be finite, means finite number of elements has to be present in that particular group. Then example is G is equal to 1 comma minus 1 under the operation multiplication is a square root of unity. Then second example is G is equal to 1 comma omega square under the operation multiplication is a cube root of unity. Then suppose if it contains a n number of elements, then it is denoted as a order of G is equal to n. Then we'll move to the infinite group. A group G is said to be infinite if it contains the infinite number of elements and order of the group is also infinite. Example is, it is a set of integers under the addition, real numbers under the addition, complex numbers under the addition. So this is an example for the infinite group. Then important note under the group is left cancellation law, right cancellation law. That is, if G comma star is a group and for all ABC belongs to G, then A star B is equal to A star C. So A is cancelled on both the sides. It is cancelled on the left side. Therefore, my answer is B equal to C. This is the left cancellation law. Then second one is B star A is equal to C star A. Here A is cancelled and which is there in the right hand side. Therefore, it is a right cancellation law. Next, theorem 1. So based on the basics of the group, let us consider the theorem. So based on the cancellation law, let us go for the theorem. Prove that cancellation laws holds in a group. If G is a group for all AXY, that is the element of AXY from the group we have to consider, and since we have to prove it for a cancellation law only, which is holds in a group. So already discussed concept is left cancellation law, right cancellation law. Let us consider that. According to left cancellation law, we have Ax is equal to Ay. So A is cancelled on the left side, therefore X is equal to Y. Then Xa is equal to Ya, then A is cancelled on the right hand side, therefore X is equal to Y. So given, let us consider Ax is equal to Ay, and let A inverse be the inverse of A in X. So uh, what we have considered is Ax is equal to Ay, operating A inverse on both the sides. So we will be left with A inverse of Ax is equal to A inverse of Ay, that is multiplying A inverse on both the sides. So bracket for the previous step was for Ax. Here in the next step, let us take the bracket for A and A inverse. This is according to the associative law. So that is bracket can be changed, and so that it is not changing the original values. So for the RHS side element, the bracket is for A and A inverse. So A and A inverse becomes a E here, as we have already said. So with the X, and in the RHS side, A and A inverse E with the Y. So A is cancelled on both the sides, X is equal to Y. Next, again, XA is equal to YA. That is, we have proved it for in the previous case, we have proved it for a left cancellation law. Here in the next case, we are proving for a right cancellation law. XA is equal to YA. Consider XA is equal to YA. So again operated A inverse on both the sides. So then we'll be getting or associative law is applied here. The bracket becomes for A and A inverse. So on the RHS side also, bracket is for A and A inverse. Therefore A and A inverse becomes a E. Therefore my answer will be X is equal to Y. Next theorem is inverse of an element in a group is unique. We have to prove it for inverse of an element. If possible, let A and B be 2 inverse of X in G. So A is the inverse of X. So that is, consider an element X. A is acting as 1 by X here. Instead of 1 by X, we are taking as a. Therefore, Ax, that is, it's like 1 by X into X. So in the place of X, in the place of A, we can also take it as 1 by X. Therefore, Ax is equal to Xa, which is equal to E. So it is like X into 1 by X here, which is equal to again X into 1 by X. X into 1 by X becomes 1. Usually we will be taking X into 1 by X becomes a 1 here, but in a group we are taking as a E, as we already said. Take another element B here, which is also again a inverse of the X. So similarly we can take it for a Bx is equal to Xp is equal to E. Again B is acting as 1 by X. Therefore from 1 and 2, equation 1 and 2, so Xa is equal to Xp. That is, considering Xa is equal to E in the equation number 1 and Xb is equal to E in the equation number 2. So we can equate for equation number 1 and 2. Therefore we have a Xa is equal to Xb. Therefore X is cancelled. Will be left with A is equal to B. Again, from the equation 1 and 2, consider Ax is equal to E and Bx is equal to E. So considering Ax is equal to Bx, cancelling X on both the sides, will be left with A and B. So which is according to the right cancellation law. Therefore, inverse of an element is a unique in a group. The third theorem is again identity element in a group is a unique. So we identity element we are considering is E here. So we have to show it for E is equal to E inverse. So let E dash is equal to E. So nextly, the identity element is a unique, we have to say, and also we can consider the unique element E and E dash. So E dash is equal to E, once we have to take. Another time we can take it as a E dash is equal to E dash, because we have already said that E is equal to E dash. But E dash is a unique, it's a unique element of G. Therefore E dash is equal to E and E dash is equal to E dash. So E dash is there on both the functions. So therefore, we can say that E is equal to E dash. Therefore, identity element is unique in a group. Next, let's concentrate on the definition of the abelian group or the commutative group. So it is the group has to be said with the abelian group, means it should satisfy with the commutative law. Commutative law means A star B is equal to B star A for all AB belongs to G. Then based on the abelian group, let's go for the theorem. Show that every group G with identity element E such that A square is equal to E for all A belongs to G is abelian. So for that, let's consider our two element A and B here. Then consider AB square is equal to E. So split the AB square function as AB into AB, which is equal to E. So according to the associative law, let's change the bracket here for B and A. Then A and B, let it be as it is, which is equal to E. Then again multiplying B on both the sides. So next step, again multiplying A on both the sides. So again, according to the associative law, let's change for a bracket here for A and A, B and B, BA, which is equal to A and E with B. That is, we are grouping the elements using a bracket. A and A becomes A square, B and B becomes a B square, then BA as it is, which is equal to AB. Why it is only the AB? AE is there in the previous step, because since it is a E is an identity element, so this is associated with the A, therefore it's just a we are going to get it. So therefore again A square B square, according to the theorem statement, we have to take it as a E here. E again let's go for the theorem statement, that is A square is equal to E they have taken. So in place of A square we can take it as a E, in place of B square we can also take it as a E. Therefore BA as it is, which is equal to AB. So BA is there along with the E, therefore just we can take it as a BA, which is equal to AB. Therefore we can observe here in the LHS side BA is there, in the RHS side AB is there. This is nothing but it's a abelian group, that is A star B is equal to B star A. This is according to the abelian. Nextly, go for the theorem 2. So prove that a group G is abelian if B inverse A inverse BA is equal to E for all AB belongs to G. So B inverse A inverse BA is equal to E. Let us consider for this, and we have to prove it for a G is abelian. So what is the operation we are doing for a first equation? B is multiplied on both the sides. Nextly, B and B inverse becomes a E, right? B and B inverse means B into 1 by B is nothing but E. Then A inverse as it is, BA as it is, B into A, E becomes a B. Then A inverse BA with the E becomes just a A inverse BA, which is equal to B. Again, multiplying A on both the sides, then again A and A inverse becomes E with BA is equal to AB. Then BA with the E becomes BA, which is equal to AB. Therefore, so you can concentrate, again it is abelian. So A star B is equal to B star A. Similarly, we can prove it for another theorem. So xy the square is equal to x square y square, which is again a abelian.